Okay. Good morning. So, today's topic is 4+2 cycloaddition. All of you have studied, right? This is a very powerful technique in organic chemistry, especially when you are planning to construct a 6-member ring system. 6-member ring system, this is one of the most powerful reactions, simply because it is versatile. You can have all kinds of these dienes and dinophiles, and the reaction is so useful. You can have stereochemistry fixed. You can also make acyclic compound, means you make a cyclic compound first, then you cleave the cyclic compound. You can get an acyclic compound with stereo defined double bonds. So, then of course, you can extend these by what are the possible extensions. Possible extension could be that you can also do the reverse Diels-Solder reactions. If you have reactions, you do some synthetic manipulation, you can reverse Diels-Solder reactions. So, that means additional reaction, that is known as Alder Lauder. No. If you have a combination of Diels-Solder reactions and the reverse Diels-Solder reaction, that is known as Alder and Rickert reaction. We will come to that. So, that means these are all the different ways of looking at the same reactions, and when you say Diels-Solder reaction means 4+2 cycloaddition reactions, all of you know, right? 4 signifies what? Number of pi electrons or number of atoms or what? Well, both, but primarily actually the number of atoms. Okay, if you go to the Young Fleming's books, he says both, but normally when you say as you go on, you will see that actually it refers to the number of the atoms participating in the reactions. Okay. For example, there is a class of reactions we will also talk about in the next class, that is called 3+2 cycloaddition reaction. So, we have 4+2 is one of them, right. Then and there is a class called 3+2, also there is a class called 2+2, and then there is all kinds of 4+3, then 5+2. So, if you see the number, then there are other higher order cycloaddition reactions known as higher order cycloaddition reactions. What you see here, then when you say 3+2, then how many electrons are participating?
4.
Not really, I mean 4 and 2. So, it is essentially actually 4+2. So, that means actually this here 3 actually refers to the number of the atoms. So, we will all talk about it, but when it comes to the Diels-Solder reactions or the 4+2 cycloaddition reactions, what is the problem and what is the usefulness? First of all, as I said that in the Diels-Solder reaction, I think probably the most versatile reaction in organic chemistry. I mean, we would not see any other reactions actually is so versatile and useful. I should say versatile and useful. You can have all kinds of the variations in the diene part, all kinds of variation in the dinophile part. You can the diene could be built into the cyclic system, it could be all acyclic, then polycyclic, all kinds of things. Also the Diels-Solder reaction can be inversed electronically, right. Many of you know that inverse electron demand Diels-Solder reactions. The traditional concept that diene should be electron rich and the dinophile should be electron deficient is no longer really rather acceptable. It could be the otherwise. The diene could be electron deficient and the dinophile could be. So, you have all kinds of, that means flexibility, but you have to know and where to start from and what are the difficulties. That means, well, those who will be doing the calculation, DFT, all these things, they will find the LUMO and HOMO and all these things, but eventually it comes down to the working out the whole thing in the lab. So, nobody knows actually what will happen. So, how do you know? How do you extrapolate? That means, you have to have a starting point. Okay, this reaction takes place. So, we can go on to the next. So, again by using the organic chemistry knowledge, electron donation, electron resonance effect, hyperconjugation, all these things. Okay. And then also you have to look at these reactions in terms of the reaction conditions. There are varieties of reaction conditions actually for the Diels-Alder reactions. What are the reaction conditions? The way you do the reaction. How do you do? Just mixing up is not enough many times. You have to all kinds of the variation. That way the reaction is pretty versatile. What are the reaction other than mixing the two reagents? Lewis acid, fine. Lewis base, no. Heat, that is somewhat like mixing, okay. High heat, high temperature means a sealed tube. Anything else? Photochemical, how can you say so? Because you have been learning all pericyclic reactions, the Woodward-Hofmann rules, all these things, and suddenly you said photochemical reactions. No, that is not acceptable. Okay. So, likewise, then there is also a reaction called high pressure Diels-Alder reaction. See, high pressure, we will have an example, one or two examples actually. High pressure, I think all of you understand the name of the building where I stay, that is a high pressure building. Actually, the genesis is that though. The person who worked there actually he worked for a person called W. Noble or somebody. He did high pressure Diels-Alder reaction, Professor Palith. Okay. And all of but theoretically you can understand the two molecules are combining to a simple, there is activation volume is decreasing when you go from the starting metal to the product. So, obviously, that if you have a high pressure, then that would assist the reaction. So, all these things are, that means it is a very versatile, very flexible, I mean you can do all kinds of manipulations. Then the last extension of Diels-Alder reaction, extrapolation or extension or whatever you say, is putting the heteroatoms in the backbone of the diene or dienophile. You just put on heteroatom. When you say heteroatom, nitrogen, sulfur, oxygen, all these things can be done, but then there is a problem. What is the problem? That you have to know. For example, pyridine is commercially available, it is a gas, right? It is used in the industry, and what else? And isoprene is a liquid. So, that means they are pretty stable, but when you have an aza-isoprene, it is unstable, very unstable. It is very difficult to make, absolutely difficult to make. So, you have to go to the heterocyclic chemistry, and all of you know, right? All of you know that furan is a diene. So, furan is a diene. So, let us begin with the examples what we recently did in our lab, and this is the reaction. We just simply mix them and just allow to sit in the room temperature, and thus in the ether solvent. So, all of you know what is the product, right? The way I have drawn, it would the furan acts as a diene and the malic anhydride. So, and the product that one can quickly write, I will write the linear form, and all of us know that it is an endo exclusively, and so what you will get? You will get the cyclic compound, right. This is all known. Then what to learn from here? That is a diene which is compatible with malic anhydride, that means a carbon-carbon double bond, that you have to note. Okay. And malic anhydride is one of the finest and most reactive dienes, dienophile rather. If you just substitute with an ester, that is less reactive. Okay. And then of course, we wanted to have this corresponding anhydride, ethyl substituted phthalic anhydride. This was done very recently in our lab. So, how to do it? From here to here, if you just again do a calculation, I mean there is no change in the oxidation number, right. If you look at this, is okay, this portion, right hand portion is same, this portion the benzene ring constitute oxidation level 4, and here also you have this is 2 cycle 2, 1 double bond, 1 heteroatom, and right 2 cycles, 1 double bond, 1 heteroatom, what else? 1. So, should it be all right? Okay. Any case, you can just we can do that, but what we did, we just basically you do not require any oxidizing agent or reducing agent, just simply acid, but you have to mind it what acid. In this case you have to use concentrated acid, and that would give you the corresponding dehydration product, etc. Okay. So, that is a clean reaction. Now let us say we will use the similar kind of chemistry, but in the preparation of, let us say, vitamin B6. Vitamin B6, what is it? I think many of you know. I think we are included in this 4th year class, right? It's a pyridine derivative, right? Pyridine derivative. What is the other thing you have to note about this vitamin B6? You have lot of OH groups here. There are 2 OH groups. This is pyridoxine. This is called pyridoxine. Pyridoxine, and what else? The striking feature, that you have to remember. What is the striking feature of vitamin B6? It is a pyridine derivative. Now, actually 3-hydroxypyridine. How do you make 3-hydroxypyridine? Tough, right? So, then and it is a substituted substituted, and as you can see here, I mean all the substitutions are contiguously placed, 1, 2, 3, 4, all these things. Okay. So, such a system is difficult to make. Obviously, the choice is what are the, I mean other than something like typical electrophilic and nucleophilic substitution reactions. If you have a right starting material, you can go to the product, or else you have to devise a new synthesis. How do you do the pyridine synthesis, for example? How do you do a pyridine synthesis? We will talk, I will, but I think this semester I will not be able to talk about the ring constructions of the heterocycles. If you continue means research scholar I am talking about. So, we will talk about the actually these ring constructions, pyrrole, pyridine, and a few systems. Okay. How do you, let us say in general, how do you synthesize a pyridine nucleus other than starting from a pyridine? So, how much do you recall from your BSc class? Pyridine, hands, no, but by knowing the name is not enough. So, you have to talk in terms of the bonds and the mode of reactions. Hunt's, yes, Hunt's pyridine synthesis is perfectly all right. Hunt's pyridine, okay, we will come to that though. Very briefly, I will just tell you. Basic and essential reaction in pyridine synthesis is the reactions of an amine with a carbonyl compound. It could be a carboxylic acid, it could be an ester, it could be a cyano, and amine, as if amine is nucleophile, and one of these carbonyl groups from these different functional groups could be the acceptor or electrophile. So, this is the essential mode of forming a pyridine. Okay. That means like if we can make, for example, if we can make sort of a furan kind of molecule here, and is acetate, and this is sorry, this is again acetate here, and OMe, this is OMe, and this is NH and acetate. So, what does it tell you? If you hydrolyze it, actually if you hydrolyze it in presence of acid, what do you expect? You expect a molecule of this kind. This is OAC, this is OAC, and this is now aldehyde, and then this one is a the middle one would be ketone, and then you have methyl group, and this is NH. So, this is how, I mean, this is a hypothetical one. That means, basically what you do is in hydrolysis. Then if you count the number 1, 2, 3, 4, 5, 6. So, what is the essential key step? Essential key steps, amine is reacting with an a electron deficient carbon of carbonyl groups. In fact, this reaction takes place to give this pyridoxine in one step. But then if you look at this one, and we know the basic thing. So, if you take acetate here, and I think all of you understand what is the basic requirement here, NH, AC and the methyl. So, you have to functionalize at the 2 and the 5 position to giving this molecule, right. And how to do it, I think all of us know. What is that? Bromine and methanol, typical bromine and methanol reactions, so oxidatively adds to this one. So, sorry, on the here bromine and methanol. Now, how to make this? This is what that means. You have to this is a way of making actually functionalized furan. How to make a very functionalized furan? Typical, we are not going for the by the typical way of doing it. I think all of some of you have studied, right, in 4th year. I gave an example, I do not know whether you recall or not. This is also taught in BSc, furan 3,4-dicarboxylic acids. How do you make furan 3,4-dicarboxylic acids? Starting from furan and what else? Diethyl dicarboxy, no, acetylene dicarboxylase. So, acetylene dicarboxylase, that is what you have to do. That means, so very similar to that, what you have to do, you take the furan, and then here this amine is well known, right, and if you react this with we call sometimes we call dead, right, diethyl acetylene dicarboxylic acid. What does it tell you? It tells you that this okay. So, if you do so, what do you expect? You expect, I will write linearly. So, you will expect a reaction. So, I will write E as the ester, and so then this amine and this, then you have double bond, right. Then what? But see, you have to actually see many things here. You have many things. What do you learn from here? That acetylene is an important one. Acetylene is an important reacting partner. Furan cycloaddition reaction is restricted to either highly electrophilic dinophile or acetylene. You will see there are some limitations. It is not that very versatile in case of. So, either furan has to be very reactive or the dinophile has to be very reactive, that is it. So, acetylene is compatible. One could have, let us say, taken, let us say, diethyl maleate or dimethyl fumarate, etc., but it is not taken here. And next thing that you have to know, that amine could have reacted with the ester to form corresponding amide, that is not being formed. Simply because just these are all things you have to know, you have to have experience, because homolomo things will not tell you which one would react faster, which one would react slower, but from experience you can make out that the reaction between the amine and the ester is much slower, requires very high temperature. Somewhat at lower temperature this Diels-Alder could be done, and then of course you have other things like acid, etc. The next step, I think all of you know, is somewhat a repetition. If you have this hydrogen and catalyst, only one of the double bond would be okay, and the one that is in hydrogenation case, the one that is actually more exposed to the catalyst. So, that means this one would be reduced. So, and the rest remain as it is, and H2 and this, and then of course, then you do a retro-Diels-Alder reaction, right. Retro-Diels-Alder reaction that loses this ethylene, and then you do this acetylation. Then you this acetylation, what is the standard protocol? Acetic anhydride and pyridine, but nowadays you use something else, right. So, that means this example tells you what, that furan can be reactive provided the acceptor is a triple bonded one. And then, but there are cases, for example, very quickly, let us say like this is a case here. Also you will see that it can also triple benzene, all of us know benzene also is reactive, even more reactive than an ordinary triple bond. So, if you can produce a benzene, normal is, there are many ways, but the conventional one is sodamide and a little bit of temperature, at high temperature, then actually the reaction is done together, actually in one step, I should say. Sodamide actually is one step reaction, all of you know. So, what is the product? I think all of us can write. The product is a cycloaddition reaction. Cycloaddition reactions, it first forms the triple bonded OMe, and then this furan reacts. Now, you see the furan can be compatible with this alkyne, that is it, nothing else, it is a triple bonded one. And now you get a bicyclic compound, it is a bicyclic compound, and this sort of molecule has been in the literature for a long time, but people have begun to use this, because normally this oxygenated naphthalenes are difficult to make by routine procedures, and then you do all sorts of reactions with, let us say in this case, this concentrated HCl and methanol gives you the aromatized product, and basically one naphthol is produced. Mind it, these are all things you have to just, when you write a reaction, you have to take note of the other selectivities. For example, concentrated hydrochloric acid methanol condition, the OMe groups is not lost, does not undergo demethylation, which often seen elsewhere. Okay. Now, what else? After alkyne, so the first was the simplest alkene, that is maleic anhydride, second was alkyne, third is a special kind of alkyne. Then what next you can think of? What next? Okay, furan is common, because it belongs to the heterocyclic chemistry. So, you will have a furan. Now, what we will try to see the selectivity. For example, you have a diene, regular diene, then there is no conjugation, that means CH2, and then you have a furan now, it is a substituted furan. So, this. So, that means you have two diene component, furan is a diene component and the isoprene unit is a diene component. Between the two, which one is more reactive? That is what you have to see. Okay. This example I am writing here will also tell you is a special kind of dienophile. After alkyne, one can think of, I think those who know very well, that alkynes will have very similar chemical property with allenes. Okay. And if you react this with very uncommon reagent, barium, actually this is known as barium manganate. What is the use? Barium manganate is a selective oxidizing agent. Normally it oxidizes the benzyl allylic alcohols, but in this case you have two allylic alcohols, and one is the secondary, one is the primary, and which could be oxidized, that is it, nothing else. Okay. So, that means other than barium manganate, what else do you know for active MnO2? Okay. So, that means there are not many selective oxidizing agents for allylic oxidation, but barium manganate is a very useful one. I have used, and this is easy to prepare also. You can prepare in grams and grams. So, now the next answer. What is the next answer? That which one would be reactive? So, that means this example tells you that allylic ketones also is compatible, and in this case the reaction takes place with the furan part, and then I will not write the rest of the things as it is. And so, what we will see then this is double bond, and then you have this OH, and this is the ketone part, and then the other part, this is the other diene part, that diene part, this is regular. This sort of reactions has been utilized in the synthesis of a natural products called eleutherovine, something like that. Okay. So, that means the reactions are useful provided you know the actually how to use it, and you have to take the risk. What else? How do you verify? How do you verify? How do you extend this sort of reactions? We have seen, right? We have seen the reaction where the furan is less active than compared to the other dienes. Okay, but if you have activated dienophile, that can be done. Then again you have a inbuilt diene where you have cyclic diene and cyclic diene, but you see that furan is more reactive. Now, what else can you do with this sort of cycloaddition reaction? Let us say you have a very unreactive dienophile. Probably many of you do not know this cyclohexene is not a very good dienophile as far as the Diels order is concerned. And so, I write here a little complex molecule, and this was made in connection with the total synthesis. You just write all these things, but essentially what you see is a cyclohexenone. Hexenone, as I said before, is not a very good one. For example, if you try to react with cyclohexenone and isoprene, okay, the reaction does not go very well. So, you have to use all kinds of acids and Lewis acids, all these things, but the yields are not very good. One of the reasons that the cyclohexenone polymerizes, fine. And but if you try to let us say do the Diels order reaction with furan, so what is your prediction? So, let us say if you have a sort of a furan molecule, so should they or should it react with this dienophile? Okay. If not, then you have to activate furan ring. How do you do activate? How do you activate the furan ring? Make it like how do you activate alkyne? Make it strained, means put it in benzyne form, then it becomes more active. Similarly, how do you make furan part very active? That is one of the reasons. Yes, it is possible, electron bonding, that is a traditional one. The other way is to look at this, just make a system which is a little strained, uncommon. Okay. This benzoisofuran, and obviously from the electron density, you see after the reaction the double bond would be inserted into the benzene ring, and you will get this is actually less aromatic than the corresponding benzoisofuran. Okay. And by the way, so obviously then you get I will not write you get the Diels order product, and this has been this has been taken to one natural products called halina or quinol. Okay. And probably in this connection, let me tell you something. I think this is commercially probably as I recall the molecule with this 1,3-diphenyl benzoisofuran is probably commercially available in all this catalog, and it has some utility in biochemical system. What is the possible use? Possible use is actually it is singlet oxygen scavenger. Whether if you are carrying out a reaction and you are let us say postulating that okay, the reaction is proceeding through singlet oxygen, you just trap it. That means singlet oxygen undergoes Diels order reaction Diels-Flatt reactions in this. So, it can nicely trap it as endoperoxides. Okay. So, that is it. That means, either you can activate furan or you can activate this, but mind it, the furans are not very good intramolecularly for alkylic double bonds or alkylic dienophile. One of the it is a very nice synthesis though. Actually, when we are graduate student, we studied this. I will tell you something. This is a molecule, very simple molecule apparently very simple molecule, and name is cantharidine. Cantharidine. The structure is looks very simple, right? That is it. Then this is a natural product obtained from beetles. Okay. Beetles, I think all of you know, right, what it is? Huh? An insect. Dekhecho? How have you seen it? Huh? A picture. Okay. But I have seen it actually. I used to live in a ground floor quarters, so I used to see plenty of them. Okay. So, this is not this is, so there is natural occurring, but interestingly is useful too. It is known as a blistering agent. You know what is the use of, what could be the use of blistering agent? Suppose you have a solid tumor, benign tumor. How do, I mean, one of the ways is to do the operation is just to remove it, just to do the surgery and remove it. Other way is to inject with a blistering agent. So, it will form a blister and then automatically slowly disappear. This is one of these possible potential candidate for the as blistering agent. Someone said it is being used, but yesterday I looked at the Google, I did not see, but it says that there is it has a property to create blisters. Okay. Any case, for us is synthesis. How do I do? Very simple, right? Apparently, it looks that this could be done from this furan, and in this case this dimethyl malleable anhydride. Believe me, the reaction does not work, and this reaction does not work, and this reaction was tried by my grandfather. Do you understand what my PhD advisors, professors? W.G. Dowman at Washington University. Okay. The reaction does not do, but in 1980 he reported the reaction to be successful. So, what can you do? What could be the major possible, I mean, reason why the reaction failed? Actually, dienophile is weaker somewhat because of the electron density is reduced because of the methyl groups. That is number one. Number two, I think in the transition state steric effect. Steric effect probably was. So, what he did, he just made a small twist in the requirement. So, like you have studied before, if you just join the two tails and put it in a cycle, that becomes less sterically hindered, right? Remember this Dabco and this triethylamine, which one, right? Which one is more basic and which one is less basic? Should I write or not? This is
triethylamine and
Dabco or corresponding azide, like bicyclic compound. I think this one. This is not really Dabco though. Quinidine, right. So, simply because if you are this is now tightened on the one end, so it is more basic. So, exactly that is what we did. They put these two methyl groups, and but you all know though that this sulfur can be very easily removed just using ranitidine. So, then obviously the reaction was done, and you will see. solvent is methylene chloride and pressure is 15 kilobar. 15 kilobar. What does it mean? 15,000 bar. How dangerous it is. We had a high pressure technology. When I joined in 1987, I asked the teacher who used to work, and what is the pressure here? And any guess what could have been the pressure? How do you increase the air pressure? You have to have a booster, compressor. Okay. So, the compressor used to work, but you have to have a pressure gauge, and pressure gauge is to record not, I mean it was, I have to do the little calculations, definitely less than 1000 kilobar, sorry 1 kilobar. So, it is 15 kilobar, and probably you have not seen the lab. I happened to see the lab in US in my university, and that the lab is basically like any other lab, but the roof was made of a glass. So, reactor was there. So, if anything happens, actually it will go to the top. Okay. So, that was the lab, but nobody has done the, I mean in my tenure nobody has done this experiment, but here also the pressure is so, but he had the venture to do that. Okay. 15 kilobar pressure, and the reaction was successful. The reaction was successful, and as you can expect, but there is a little problem. It was not endoselective, it was actually exoselective, and this was the major product. The other then of course, this other one was the isomer. Other one is the isomer. Okay. So, this other isomer, endoisomer, and now what? Runny nickel and other solvent is ethyl acetate, and of course, little heat, and you get to this product. So, essentially what do you do? Just what do you do? Just 2 reaction and 1 Jacks paper, and so by just doing 2 reactions and getting a Jacks paper is tough. And so, now you can see the imagination part, experience, everything, facilities, all these things is good to this. And this was published in 1980. 10 years after, there is one scientist called Paul Greco, student of Gilbert Stork. He made a quick, he made a trick. Without going through the pressure, he could do the same reaction and exactly same ratio, and the yield was also fairly good, 70%. And what is it? Any idea? No, normal pressure, room temperature. Again a Jacks paper, yes, Lewis acid. What Lewis acid? No, that is what, in fact, the Lewis acid is 5 molar lithium perchlorate. 5 molar lithium perchlorate in ether, that is it. And the lithium perchlorate is available, commercially available. It is obtained from this Aldrich. So, you do this, just substitute this, the reaction goes to same product, same ratio, same products and same ratio, the yield is fantastic. Yield is fantastic. Okay. Let us continue with little more, like one more reaction. Probably this would tell you something additional. The reactions I am writing now is an intramolecular version. Once again, it is a seven membered ring with a carbonyl up here, and then double bond, methyl group, and a sulfur and methyl up here. Heat it, what do you get? So, 7-membered ring, and then you get a 6-membered ring, double bond, this furan, SMe, and then acetate unit, that and this, then you have this nitrogen up here. So, you have this. Okay, then you can go on. I think all of you can understand. Basically, what we are looking for? We are looking for a diene and a dienophile, and in this case what you see that diene is little active because of the substitution of the sulfur. So, diene active. Now, mind it, this is not a dienophile though, it is not a regular dienophile, neither it is conjugated to an electron withdrawing group or anything, right, nor is a triple bond, this is just a single double bond. So, what is the driving force for this reaction? Intramolecular effects. So, likewise there are plenty. I think I have one more example. I think this is a nice example I will give you. This that means if your diene is not very active, if your dienophile is not very active, if it is an intramolecular reaction, there is a possibility the reaction can take place. That is what you have to remember. That is it. Okay. And this is something very interesting. This example will tell you many things. Actually, this is again here you have an olefin, and these are the typical natural product skeleton, that dioxolane. Then you have amide group here. This amide is functionalized with 4 carbon. Then this is now connected to oxadiazole. Oxadiazole means in this case 1,3,4 oxadiazole, sorry, and this oxadiazole, okay, and simply heat. That is the beauty of Diels-Alder reactions. If you have a properly designed substrate, you can do a Diels-Alder reactions. What do you do? What do you expect? So, rather, what is the difference between the earlier among the rather difference with the earlier examples? Here you have a furan by diazafuran. So, when you say nitrogen, what do you, all of us know, right? It becomes electron deficient compared to furan. So, now you have an ester group up here. Then you have a nitrogen which is conjugated to carbonyl. That means this is also somewhat like an electron withdrawing group. That means essentially this diene is electron deficient. So, unlike the furan, it is electron deficient. Then what you require then? Electron rich olefin, and that is what we have here, electron rich olefin, that is this methoxy group, that is it. And what else? Then you have this intramolecular version. So, all these driving forces are in the same directions. Same, that means this electron deficient, this electron rich, intramolecular, and the reaction takes place. Of course, I will write the full structure. So, you should just see here, I think all of you can write, right. So, it first form that means OMe, and this is the aromatic portion, then what? This nitrogen and this oxygen, right, oxygen, and adjacent to it you have this ester here. What else? That is it. Then actually under thermal conditions, actually you lose methanol. You lose methanol. So, you will have something like nitrogen, then oxygen up here, and then ester here. Now, you can see what is going to happen. It is a retro Diels-Alder. So, it is a Rickert procedure, Alder Rickert procedure, and loss of nitrogen. That also you have to note. See, I will have many more examples. Probably we will talk about all these things in the next class. This nitrogen is one of the nice loss of nitrogen is a very important driving force in cycloaddition reactions. So, once you have this, that means you have methyl group and you have these homoallylic kind of appendage. What next? So, actually one more the same process with this double bond, one more, so the same process with the double bond, and so what you will see, you will see this so double bond here, this ester here and this. So, these are all these reactions it is carried out little elevated temperature at 230 degrees centigrade, and what else you can think of, basically one more intramolecular Diels-Alder reactions between these furan unit and the olefin unit. So, once again this is an example to show that furan, if it is unactivated, then the dienophile has to be activated. If they are not activated that way, then you have to put them in a simple molecule in intramolecular fashion to give the corresponding product. Okay. What next? Cycloaddition. We have been talking about cycloaddition. So far we have talked about this furan, talked about this oxadiazole. Okay. We have seen different examples, alkynes, alkenes, and if it intramolecular, the reactions could be done. And what you see here, this if you then and actually this reaction does not stop here. The reaction actually goes straightway to the corresponding benzene derivative with a polycyclic structure, and so actually you get to these sort of compounds, this sort of compounds. Okay. What else? What else can you do with these cycloaddition reactions? Just give me a suggestions. So, as if we have learned everything, then what can be done? What modification? Basically, I mean most very few fundamental reactions are being discovered, right, these days. All these fundamental reactions are already discovered. We have been just modifying, manipulating all these things. So, okay, how do we extend this sort of Diels-Alder reaction to other? Of course, one of these ways to put more number of heteroatoms. You have put 2 heteroatoms here, you have made it electron deficient. Okay, so dienophile should be electron rich, right? And so there are cases, for example, very recently, this is in industry, the vitamin B6 is produced by Diels-Alder reaction. I do not know whether you know or not. Vitamin B6, the one we showed that, okay, pyridine derivative, and is but the dienophile, the diene is, what is the diene? Diene is oxazole. Oxazole means it is a 5-membered ring with, of course, oxygen and nitrogen at the 3 position, nitrogen is the 3 position. So, nitrogen is the 3 position. If you begin with oxazole and let us say I will put it here, it's hydrogen, and this is, let us say, methyl group here, and this O and ethoxy, and this the carboxylic ester, and see whether this reaction would go or not. That is what we have to have some idea about this. Our idea comes from the background, we know. So far we have known all the details about the furan chemistry, and also one example we have seen, that was an intramolecular version, but this is an intermolecular version. Now you have to evaluate whether this reaction is a feasible one or not. Of course, once you have written here, it means it has to be feasible, but what is the background? It is very similar, but with nitrogen. So, what does nitrogen make difference here? What do you expect? Nitrogen makes you a little electron deficient, right? Electron deficient, but that is compensated by electron rich the electron donating group, ethoxy group. What else? That is what you have to remember. in very early classes actually we talked about the effect of nitrogen. Instead it can alter the pKa values. What else? It can, let us say, from a very simple thing, from benzene to pyridine. What else? What do you expect? What change do you see? The electrophilic sites are changed, the nucleophilic sites are changed, that means, and if you do homolumo, what will you see? Resonance energy is less. So, if the resonance energy is less, that means the propensity of these heterocycles to undergo Diels-Alder reaction is more, and that is what happens. That is what happens. Okay. So, the reaction actually goes on to this. I will just quickly write. Goes on to produce this straightway to this methyl group here. I think should I work out the mechanism? Okay. Mind it, the reaction very uniquely, I mean previously it was done in industry, okay, by thermal heating and a little bit of acids etc., and very recently someone has done it with an unusual catalyst, and he says it is a commercially cheap catalyst. What is this? ND, neodymium triplet. Neodymium triplet 40 mole %, it gives you straightway this Alder Richter, means Diels-Alder followed by all these cyclization etc. Now, it is not retro Diels-Alder. If you just work out this mechanism, you will see it is not a really Rickert reaction. It is then finally, you have this rearrangement taking place, right, under the presence of acid. So, you will have ring opening, then the ethoxy loss in under the presence of the acid, and the yields are very good, and what you get is a nice Kempom paper, and this was published in 2012. See, it is the same reaction, absolutely, just he has made sure only thing that what he has found, this neodymium triplet, and the yield is good in one step. That is the beauty. In other cases, you have to do the Diels-Alder reactions, then you have to do acid catalyzed isomerizations or cleaving etc. to get to this compound, and this is a nice precursor. And that is not all. How do you make this though? That is oxazole. How do you make oxazole? That you have to know. This is standard protocol. Standard for oxazole. Oxazole means, so you have this one, let us say this one for example. How do you make it? There are plenty of ways. Probably many of you by now know there are two books in heterocyclic chemistry. Name reaction in heterocyclic chemistry, a thick book, one more that volume 1, and one more volume recently has come out, volume 2, that is lying in my office. So, I mean there are so many things to be learned, but we normally we do not burden ourselves by learning many things, right. We have to have some systematic way of looking at. How do you look at? How do you look at? Coming back to the erythrosynthesis class, there are three ways actually. These days this matter is little simplified because of the SciFinder. So, you go to the SciFinder, if SciFinder works perfectly all right, but if you want to do some research, like you can do this, there are 5 steps, you can do it in 1 step, that sort of thing you can do. But if you want to get your compound done, that is important. If you have a fixed target, you want to get that compound, then the situations are difficult. In fact, we tried to make a 4-ethyl phthalate, we could not do it very efficiently though. We did it, like the very first example I showed you, ethyl furan plus malic anhydride gives you the corresponding anhydride. But when you convert this into phthalate, means one of the CH which should be reduced to corresponding carbonyl group, one carbonyl should be reduced to the, then we had actually 2 products, both the isomers. On the carbonyl adjacent to ethyl was reduced, and this IOFN also was reduced. So, we could, that means that efficient, that synthesis was not a good one. So, how do you make it? Let me say again erythrosynthesis, right, and erythrosynthesis, what is the major, what is the erythrosynthesis measures, there are the very first step, what do you do in erythrosynthesis?
Identify the pattern.
Good, very good, at least Officic knows at least. Okay. Next, that means you have to see the structural components first, identify the structural components, measure structural components, fine. Next step, hydrolytic cleavage. That's one, hydrolytic or oxidative, these are the typical cleavages, hydrolytic or oxidative. And third one, that should be your transform based means the reaction based. There are, as I tell you many often, rather quite often, that there are not many reactions in organic chemistry though, only handful, other than oxidation reductions, there you have very handful of reactions. I mean, if you start thinking about, we will have only Cycloaddition, this Diels-Walder, imine formations in reactions, that is it, something like this, not on the Claisen condensations. And biosystems, how many reactions do you know from which are actually occurring in biological systems, let us say. Once upon a time I used to teach actually biological chemistry. Okay. I summarized, you do not find many biological reactions, that means organic reactions in biological systems, only few, very few. The transamination, all these things, they take place through the shift space formations, and Diels-Walders are not common. One occasionally people find Diels-Walder etc. Then Claisen condensation, Cycloadditions, and few oxidation and reduction, that is it. So, that means you do not have to have many reactions to come up with a right complex molecule. So, any case, so this is what is very important, oxazole. How do you do so? I mean, just do the oxidative cleavage or the or hydrolytic cleavage. If you do the hydrolytic cleavage, what you will find, you will have the, if you break it, this is N, H and this, that is it, or a little bit fairly written. This, right. So, that means N formulated amino acid. So, that means all these alpha amino acids can be converted into the corresponding oxazole. And how do you do it? If it is in hydrolytic cleavage, how do you do? So, dehydrative cycloaddition, reverse of hydrolytic cleavage is dehydrative cycloaddition, cyclocondensation.